Let's see whether feature scaling is required for continuous features in decision trees. In general, feature scaling is divided into two types. Those are standardization techniques and normalization techniques. So coming to the standardization, it is a very effective technique which rescales a feature value so that it has distribution with zero mean value and unit variance. Okay, that is, you take any continuous feature and apply standardization on top of that continuous feature, then all the resultant values will have the mean as 0 and variance as 1. So that is what the standardization is. And the next technique is normalization. And within normalization also, we have different other methods. One of the methods is min-max normalization. So this technique rescales a feature. It rescales the feature values with the distribution value between 0 and 1. That is, if we apply min-max normalization on any continuous feature, then it transforms all the values to lie between 0 and 1. Okay, so these are the two scaling techniques that we have: standardization and normalization. So now the question is, does decision trees requires feature scaling for continuous features? So the answer is no. Okay, there is no requirement of feature scaling techniques such as standardization and normalization in the case of decision trees, because decision trees uses rule-based approach. Okay, we know that decision trees uses a rule-based approach. So what do I mean by the rule-based approach? So if you observe the decision trees, so what does it contain? So decision tree just contains, a bunch of if-else conditions, right? A bunch of if-else rules, So every decision tree will have a bunch of conditions. So it's actually rule-based. So what do we actually care in the rule-based approach? We only care whether some feature is less than or equal to some value, or if some feature is greater than some value. We only care whether some feature is less than some value or greater than some value, but we don't really care the scale of those values. I'm saying that we only care whether the feature is less than or equal to some value or not, but we really don't care the scale of these values. Okay, because that doesn't change anything while constructing the decision tree. To understand this more, let's consider an example of the continuous feature. Okay, so here I'm considering a feature f with the continuous values in this feature. So if you look at the values, we have all the continuous values. Okay, the least value in this feature is 3.4. The highest value in this feature is 39.2. Now let's say I applied the normalization techniques on this feature. Let's say I applied the min-max scaling on this feature f. So what does it do? Min-max scaling transforms all the values to lie between 0 and 1. That is, if you observe the transformed values, every value is lying between 0 and 1. If you take the minimum value, so this minimum value is transformed into 0, the maximum value is transformed into 1, and all the remaining values are lying between 0 and 1. Okay, so this is the transformation. Okay, this is the transform vector f subscript 10. So now, okay, let's say we have these two features, f and fn. Now let's see in the methodology of constructing decision tree whether these two things vary. Okay, so what do we do for a continuous feature? We take the feature for every value, okay, from min to max. So I'll take feature less than or equal to 3.4. We compute the impurity. Similarly, we take feature less than or equal to 6.4 and we compute the impurity. Likewise, we compute the impurity for every unique value. We compute the impurity for every unique value. Okay. Now let's say we compute the impurity for this feature. Okay. We compute the impurity such that fn less than or equal to 0.0. So this is one split. Similarly, we compute the impurity by saying fn less than or equal to 0.08. Okay. So again, we compute the impurity. So what is actually changing here? The only conditions are changing. Okay. To be specific, only the values are changing. Okay. So instead of writing f less than or equal to 3.4, here we are just writing fn less than or equal to 0.0. Okay. So only the values are varying, okay? But the impurities won't vary, right? Because for every feature, there will be an associated target value y, right? So let's say we have a binary classification, something like the class variables like 0, 1, 0, 0, 1. So we compute the impurity on these target values, right? So these values are not changing. So even if we change, let's say feature less than or equal to 3.4 to feature less than or equal to 0.0, the splits are not going to change. The split is going to stay the same, and the impurity for these two splits will be same, right? Because we compute the impurity only on the target values, not on the feature values. So even if we make these kind of transformations, it's of no use in the case of decision trees, because it uses a rule-based approach. So all we care is whether the feature is less than or equal to some value, or the feature is greater than some value, okay? But we don't really care the scale of these values. Irrespective of the scale of these values, we always get the same splits, and the same splits will have the same impurities. So the feature scaling is not required for the continuous features in case of decision trees. Thank you.